Now we're going to explore a technique of integration that involves a decomposition of a fraction. So let me illustrate it with an example here. Let's suppose we have 1 over x squared plus x dx. And we want to find the antiderivative. So we want to evaluate that integral. Now, notice that I'm just going to take this integrand out and just look at it. I've got x squared plus x. Okay. Now notice that I can factor that as 1 over x and times x plus 1. Okay, so we've got this fraction, and the denominator consists of a product of x and x plus 1. So what we can do is we can say, okay, let's go backwards from adding two fractions and getting one fraction like this. Let's decompose it. And we proceed as follows. We say, we think this way. When we added two fractions together and came up with this, we can assume we had one of them with a denominator of x and the other with x plus 1. In other words, we think of it this way. We added something over x plus something over x plus 1. And when we added those together, we came up with 1 over x times x plus 1. So we're making that assumption, and we're going to work. So we kind of decomposed it, and what we have to figure out is, well, what is A and what is B? We need to find A and we need to find B so that when we add these two fractions together, we get this. So let's see how we would proceed. Let's just add these fractions now. A over x plus B over x plus 1. The common denominator is x plus 1. So let's see what we would do. We have this so far. We have 1 over x plus 1 equals, now let's see here, what I need in the top and the bottom of this fraction is x plus 1. So I'm going to multiply the top and the bottom by x plus 1. See? So I'm just building up that fraction. I'm going to add it. And then over here, I need an x. So I'm going to multiply the top and the bottom by x. Okay. Now we've got the same denominator. Now I can combine the numerators. So we've got 1 over x plus 1 equals a x plus 1 plus bx over that common denominator. There. So all I've got to do now is figure out what a and b are. Well, since these two are equal and they have the same denominator, let's just focus on the numerator. So I've got 1 equals a times x plus 1 plus bx. Now, I'm going to clear the parentheses over here, and I've got 1 equals ax plus a plus bx. Now remember, this side has to equal 1. So I want to do this. I want to group my x's together. So I've got ax plus bx. Let me factor out the x. So I just did a little bit of rearranging here, put the x's together, factored out the x, and then I've got the a here. Now notice on the left-hand side, there is no x. Well, that means that if the left and right side are equal, this coefficient of x must be 0 since there's no x over here. So I've got this situation. I've got that a plus b must equal 0. Okay. Now, the constant is 1, so a must equal 1. There. So we found a equals 1. Now, this little method that we used here is called equating coefficients. I equated the coefficients of x. Of course, over here we have 0x. and then I equate it 1. It's the constant. It must equal 1. So now we got a equals 1 and a plus b equals 0. So 1 plus b equals 0. That means that b equals negative 1. Okay, now let's see how that helps us. We had this integral. We were trying to work with this, 1 over x squared plus x. This was the original integral. And what we found is that 1 over x squared plus x can be written this way. A over x, well, that's 1 over x dx. See? 1 over x plus b over x plus 1. Well, b is negative 1. So this is negative 1 over x plus 1. Like that. So what we've done with this partial fraction decomposition, what we've done with this partial fraction decomposition is we've taken this thing, which looked a little too complex for us to deal with, and we've reduced it, we've decomposed it to something that's simpler, because we know what this antiderivative is. This is the natural log of absolute value of x. And then we've got still, let me go ahead and factor out that negative. And this one is the natural log of absolute value of x plus 1. So here's what we have now. We have the natural log of x minus the natural log of absolute value of x plus 1 plus c. And there's our antiderivative. Okay? And of course, we could write this way. We could say the natural log of the absolute value of x over x plus 1 plus c. And there we have it. Now let's look at a little more complex example. We've got this integral, and we want to use partial fraction decomposition on this one. Now, it's important to note that to use partial fraction decomposition, you need to start off with the power on the bottom being bigger than the power on top. And the first thing you need to be able to do when starting this partial fraction decomposition is you want to factor the bottom completely. So here's what we have. We have 6x squared plus 10x plus 2, and I want to factor the bottom. So the first thing I would do is factor out an x, and then I have x squared plus 3x plus 2. So that would factor into x plus 1, x plus 2. There we go. So we've completely factored out the bottom. Now that's the first step in finding a decomposition for this integrand. You factor the bottom first. Okay? So we factored it completely. Now I'm going to write this as a over x plus b over x plus 1 plus c over x plus 2. Now once you do that, the job is to find a, b, and c, and we're going to do that by going ahead and adding these fractions. I'm going to get a common denominator, which of course is x, x plus 1, x plus 2. But so here's what I'm going to do. I've got a over x. What it needs is an x plus 1, x plus 2. That's what it needs, right? So I multiply the top and the bottom by x plus 1, x plus 2. Now as far as b goes, I have an x plus 1. I need an x times an x plus 2. And then c, you see how the game is played now. I've got an x plus 2. I need an x times an x plus 1. Okay? And all of that over the denominator. There it goes. So here's what we have. We have 6x squared plus 10x plus 2 over x, x plus 1, x plus 2. Now, so these two sides are equal. Notice the same denominator. So what I'm going to do is equate the numerators. So just like before. So I've got 6x squared plus 10x plus 2. And I'll just forget the denominator there for now. I'm just going to focus on these numerators. So I get the numerator up here. Now notice I'm going to multiply this out. I'm going to multiply everything out. So I'm going to get ax squared plus 3ax plus 2a. Now that's what I got when I multiplied this out and then distributed the a through. See? Because this was x squared plus 3x plus 2. Well, there's ax squared plus 3ax plus 2a. Okay? Now I'm going to do the same thing here. This is going to be bx squared plus 2bx. That's this right here. And then likewise over here. So I've got cx squared plus cx. Okay. So I've got everything, all the parentheses cleared. Now, what I want to do next is I want to group the like terms together. All the x squareds, I want to group those together. So here's what I have. I have a plus b plus c x squared. See? I just put these together and factored out the x squared. And I also want to group the x's together. So let's see what I've got. I've got 3a plus 2b, okay, plus c x. Yeah. So I've got all of those. Now let's see what's left. I've got 2a right here, right? Just 2a. Is that it? Yep, that's it. Plus 2a. There. Now, I've got all the like terms grouped together. Now, we want to equate coefficients. So notice, 6x squared plus 10x plus 2 equals this. Well, if these are equal, then a plus b plus c must equal 6. See, because that's the coefficient of the x squared. Likewise, 3a plus 2b plus c needs to equal 10. See, just set that equal to 10. And 2a needs to equal 2. So what I have now is I have a nice system of equations to solve. And the first part is easy because notice that a must equal 1. We get that from this right here. Okay? So now, you know, it's just an exercise in solving a system of equations. So I'm going to put a 1 in for a. So I get 1 plus b plus c equals 6. And I get 3 plus 2b plus c equals 10. Okay? So we continue on. b plus c equals 5. And 2b plus c equals 7. See? Just bringing the constants over. And now we can solve this. I think what I'll do is I'll eliminate the c. I'll just multiply equation 1 here by negative 1. And I get negative b minus c equals negative 5. And then I've got 2b plus c equals 7. And that means that b is equal to 2. So good. We've got a is 1 and b is 2. Now we can go back and we can find out what c is because, you know, pick any one of these equations. I'll pick a plus b plus c equals 6. So here's what we've got. We've got 1 plus 2 plus c equals 6. And this gives me c is equal to 3. So we have got our partial fraction decomposition. We know that A is 1, B is 2, and C is 3. So now that we've done all of that, we can rewrite our integral. So let's see what we've got. We started off with this integral. We had 6x squared plus 10x plus 2 over, I'll go ahead and put the originals, x cubed plus 3x squared instead of the factored part. Now, we know that that can be written as 1 over x plus 2 over x plus 1 plus 3 over x plus 2. See? Because notice that's what we had up here. A over x plus b over x plus 1 plus c over x plus 2. So we were able to rewrite this complicated looking integral into 3 small little tame integrals, right? So this is going to be log absolute value of x plus 2 log absolute value of x plus 1 plus 3 log absolute value of x plus 2 plus a constant. And there we have it. So we have successfully found the antiderivative for this thing. And then you could use properties of logs to make it look different. But that's the process. Okay, here's another example. Now, I'm going to take the inside here and factor it. Okay, so I factor out an x squared in this case, and now I have an x plus 1. Now, we want to decompose this fraction. Now, here's what you have to remember. Look at this. This factor here is squared. So we have to work up to it. In other words, we have to go, okay, this is going to be a over x plus b over x squared. See how I worked up to it? Now, if this had been x to the 4th, we would have a over x, b over x squared, c over x cubed, and d over x to the 4th. We work up to it. What we're doing is we're making allowance for the fact that when I added fractions together to get this, x could have been one of my denominators. Okay, so I have to make allowance for that. It's not just that we had x squared as a denominator and x plus 1. No, we could have had an x. So we have to decompose it this way when you have these powers. When a factor is raised to a power, you have to do this. Now, we proceed as usual. I'm going to get my common denominator and equate the numerators. So let's just skip part of it. We understand the denominators are going to be alike. Okay, for this one right here, we have a times x plus 1. Because what we need here is an x times an x plus 1. What we need here is just an x plus 1. Okay? It's already got the x squared. You just need an x plus 1 on top and the bottom. And then c just needs an x squared. See? Just multiply the top and the bottom by x squared. So we multiply the top and the bottom by x here, x plus 1 here, and x squared here. Now, let's see where we are. I'm going to clear my parentheses, so I've got a x squared plus ax. Okay? Now, this is going to be bx plus b and cx squared. Now, let me equate everything. So I've got a plus c x squared plus a plus b x. Okay, so let's see here what we got. We got the x's and then plus b. And we just set that equal to the 2x squared plus 2x plus 1. Okay, at this point, I equate my coefficients. A plus c must equal 2. a plus b must equal 2 as well. See? And b is definitely 1. So b is 1. Okay, now if b is 1, then we can immediately go up here and say, well, a plus 1 equals 2. Then that means that a is equal to 1. Okay, so it looks like a is equal to 1 as well. So a and b are both equal to 1, and then we've got 1 plus c equals 2. That means that c is equal to 1 as well. So a, b, and c, they're all equal to 1. So our integral then, we had 2x squared plus 2x plus 1 over x cubed plus x squared. We can rewrite that as, it was a over x, so that's 1 over x dx, plus b, 1 over x squared dx, and then plus c, and c was 1, so we've got 1 over x plus 1 dx. There. So these integrals are much more tame, and of course this is going to be natural log absolute value of x plus this one right here, natural log absolute value of x plus 1. And then we've got this one, which is x to the negative 2. So we have to be careful. This is not going to be natural log. We're just going to use the power rule. So we've got natural log absolute value of x plus natural log x plus 1. Now, this one, so we're going to have plus 1 over negative 2 plus 1, x to the negative 2 plus 1 plus c. We're just using the power rule for integration, so don't forget the basics. So here's what we've got then. We've got natural log x plus natural log x plus 1 minus x to the negative 1 plus c. And, you can play around with that and arrange it how you see fit, maybe 1 over x, but that's the way you proceed. Now, it's important what we did up here by building up. In other words, I had a over x plus b over x squared. Building up there, that's important because we can see what would happen if we didn't do that. Let's suppose I just had a over x squared plus b over x plus 1. In other words, let's see what would happen had I left off that a over x. In other words, if I'd started right here. So I've got this. I've got 2x squared plus 2x plus 1 all over x squared x plus 1. Now in this right here, I'm not making allowance for the fact that there was a 1 over x involved in forming this fraction. Well, let's see how it works out then. We have a times x plus 1 plus bx squared. Okay, and now we have ax plus a plus bx squared. Okay, so far so good. No red flags yet. Okay, so this is what we have. Now, notice that b is going to equal 2. No worries there. And notice a, the coefficient here, a is equal to 2, and a is equal to 1. A is equal to 2 and a is equal to 1. So see, this just fell apart. This was a disaster, right? So you need to be sure and build up to it. You have x, then x squared, and so forth. Let's take a look at one more example here. So we have this integral and we want to use partial fractions. So first thing I do is I'm going to factor the denominator. Okay, so here I've got the numerator, and then I factor out an x, and I get x squared plus 1. Now this problem, this right here differs from the previous examples that we worked through in that we have something other than a linear factor. This is a quadratic factor. So we're going to deal with this one a little bit differently. Still, we start the same way. We've got a over x, okay? And then for this quadratic factor, we're going to put bx plus c over x squared plus 1. Now this is the way we will deal with all quadratic factors of the form ax squared plus bx plus c. We're always going to put on top something, a constant x plus another constant like this. This is the approach we take. Okay, that being said, we proceed as usual. So what we have now is we have, let me just concentrate on the numerator here. We've got 5x squared plus 4x plus 2. Over here, I've got a times x squared plus 1 plus x times bx plus c. See? Just like usual, we're building up the denominators. We needed an x squared plus 1 here, so I multiplied the top and the bottom. And then I needed an x over here, so I multiplied the top and the bottom. And now I've just equated the numerators. Now let's see what we've got. We proceed like usual. We've got 5x squared plus 4x plus 2 equals ax squared plus a plus bx squared plus cx. Okay. Now I group my a's together. I group my x squareds together, and I get a plus b x squared plus cx plus a. See, that's the way that all worked out. So now we got 5x squared plus 4x plus 2. So everything's the same. The only difference is how we started the problem. We recognize this is not a linear factor, it's quadratic, so we change the numerator. Okay, so now we have a plus b is going to need to equal 5. C equals 4. And a equals 2. Oh, that works out nicely. We already got a and c. Now I can easily get b because I've got 2 plus b equals 5. That means that b is equal to 3. Yeah, so now we can take our original integral, which was 5x to the second plus 4x plus 2 over x times x squared plus 1, and we can rewrite it this way. We've got a over x. Well, a is 2, so this is 2 over x plus, let's see here, b is 3. Well, let's see. Remember, it's bx plus c over x squared plus 1. So here's what we've got. We've got 3x plus 4 over x squared plus 1. Yeah. See? So the b was 3, so I just put the 3 right there and then the 4 there. And there we have it. Now, so we've got two integrals to deal with. This one's easy. This one is just 2 log absolute value of x. But what about this one? Well, this one's going to take a little bit more work. And I think what I want to do here is split this integral up. Because I recognize the x squared plus 1 down here, that reminds me of arctangent. And then I've got the x up here, and the x squared plus 1 makes me think I can use some sort of substitution. So here's what I've got. I've got 3x over x squared plus 1. Okay. Plus 4 over x squared plus 1. So I've got these two integrals. Now I'll start here. I'm going to let u equal x squared plus 1. Then du is equal to 2x dx. See? Just straight up substitution. Now I can divide by the 2, and I get that x dx is equal to du over 2. Okay, now let's see what we have. Let me factor out the 3 halves. So I've got 3 halves. See, there was the 3 there already, and then I put the 1/2 du, and now I've got this. I've got du over u. And that's going to be 3 halves natural log absolute value of u, which is going to be 3 halves natural log absolute value of x squared plus 1. We don't really need the absolute value in there, but for this one, because x squared plus 1 is always positive. Okay, so I've got that integral. Now let me take a look at this one. This one is just going to be 4 arctan x. Yeah, so not much to do with that one. So let's go ahead and see what we've got then. We've got 2 log x plus, now let me put in this stuff, 3 halves log x squared plus 1, okay, plus 4 arctan x. And don't forget the plus c. There. So there is our antiderivative. And you can play around like usual with the logs if you want to make it look a little more compact.